2y, 2yx. So that derivative of this with respect to y is 0. Derivative of that with respect to y is 2yx. And then plus partial of g with respect to y, right? Okay, that's where we are. We're taking the partial of this with respect to y, so it's whatever the partial of that with respect to y is. But what does that need to match? That has to match this, right? Therefore, 2xy, that's this piece, must match this 2yx plus the partial of g with respect to y. So what does that tell you the partial of g with respect to y is? 0. Now what do you think we do? Integrate this with respect to y, right? So integrate this with respect to y. Look, be very careful here. Integrate this with respect to y. Integrate that with respect to y. The right-hand side is what? The right-hand side of this is just g, right? What about the left side, though?
It becomes GZ, I think. Well, no, wait, it becomes constant. It's either going to be a C or it's going to be G.
Could it have z's in it?
Yeah.
It could have z's in it, couldn't it?
Yeah, so it's
Couldn't it have z's in it? Because when we looked at this, we said, remember, G back here could have had y's and z's. We took the partial with respect to y, we got something. All we know is that when we take the partial with respect to y, we get 0. But that means we could have just z squared could be there, right? And then the partial with respect to y would be still 0. So this side is not a constant. It's something that could potentially have z's, but only z's. So it's actually some new function h of z. Okay, so where are we? All right, where was our f? We had f at one point, right? Here's what we have. Okay, now here's what I can say about f. F is equal to x squared z plus y squared x plus the g function, right? But what have we determined that the g function has to be? Just some function of z. So we know for sure now that the g function has just z's in it. We're still not done. We still haven't used one entire piece of this, right? We haven't used that. So let's take that and take the partial with respect to z. So what is the partial of this with respect to z? My next volunteer. X squared plus 3z squared. Am I not following something?
No, it's
just this, right? I'm not sure who's talking. I heard. So you're taking the derivative of this. Oh, okay, sorry. You were looking at this.
Yeah.
Okay, sorry. Yes, it is. It needs to be this, but I'm taking the derivative. I was wanting you to take the derivative of this. Yeah, I got you. Let's do this. Let's do this. Partial of this with respect to z would be x squared plus.
Wait, I'm sorry. I keep doing the opposite of everything. It's just plus h of z.
Plus h prime of z, right?
No.
The partial of h with respect to z. But this has to match what? Therefore, x squared plus 3z squared, which is what you were looking at earlier, right? Has to match this, which means that 3z squared is the partial of h with respect to z. And if you integrate both sides of this, you have h, don't you? h is z cubed plus a constant. So it's like in the beginning we said, hey, look, here's what we know f has to be, but we could have some stuff that has z's and y's in it. Then we went through all this and we said, okay, now we know that that stuff that's out here can only have z's in it. We used the last piece of information to figure out that that stuff out here is actually z cubed plus a constant. So now we can put it all together. Our final answer. Our final answer is little f is x squared z plus y squared x plus, right, z cubed, and then plus some constant, right? We could say 0, but there it is. What is the good part about finding the potential function? Like when you think you've found it, what's good? You can always check it, right? Like you can always check to make sure you got it. Just take the partial of this with respect to x, you better get that. Partial with respect to y, you better get that. Partial with respect to z, you better get that one, right? Okay? So is this a conservative vector field? It is, because we found a potential function, didn't we? But I didn't have a quick check for it, not like this, right? We didn't have this. That's a quick check to see if a two-dimensional vector field is conservative. Right now, the only way to check for a three-dimensional is to actually go try and find its potential function. I'm wondering, let's see if we can't, do y'all feel like doing this? Just making up a vector field and seeing and hoping it's not conservative and see what happens? Like why our partial integration will fail? Let's see here. Let's try and make one up. It's not hard to make a non-conservative vector field. So let's go with this one. How about xy squared. I heard 1 over x, so I'm going to put y over x. And then let's go with like e to the x times y. I'm pretty sure this is not conservative. All right? So I'm going to move fast through this. First thing I know, if this is conservative, the partial of little f with respect to x equals xy squared, right? That has to be this. Integrate this with respect to x. Little f has to be, with respect to x, half. Let me put a 2 here to make my life easier. So integrate that with respect to x, and we'll get x squared y squared plus some possible function that has y's and z's in it. Okay? You all follow me? Now, differentiate that with respect to y, which would be 2x squared y plus the partial of g with respect to y. What does that have to match? That has to match that, right? So now we have this. We have y over x must equal 2x squared y plus partial g with respect to y. Yeah?
Yeah.
I don't see that matching up very well, do you? So now we have this. Y over x minus 2x squared y has to be equal to g subscript y, right? Like this?
Yeah.
So what I'm supposed to be able to do here is integrate this with respect to y and this with respect to y. Right? Okay, can we do that? We can actually, can't we? What's the antiderivative of that with respect to y, antiderivative of that with respect to y? So this is g. This one is, what's, yeah, one, so we're going to go y squared over 2x minus x squared y squared. And what's wrong with that? What's wrong with that? Why is this wrong? Why is this already a contradiction? That's right. Remember when we said this about g? We said g could have y's and z's in it, right? But it can't have x's in it. And look at what we're saying g has to have. Y's and x's in it. So this can't work, right? So at this point, we can say it's non-conservative. The partial integration breaks down. All right, I just felt like messing with that. That's it for that section. Green's theorem. So there's a few theorems at the end of this book that are just like, like, whoa, okay? And this is one of them. There's Green, there's Stokes's, and then there's the divergence theorem. Those are the three big ones. This is the first one. This theorem is just, I hope you will agree, it's just mind-boggling. Green's theorem is a theorem that somehow connects the line integral around a simple closed curve to the double integral over the region bounded by the curve. In some way, there's a relationship between the integral that goes around a curve, the line integral, and the double integral of the region it encloses. And here's the theorem. We have to first establish what's called positive orientation. So anytime we're looking at a region with a curve around it, then in two-dimensional space, okay, this is only in 2D, then positive orientation is counterclockwise. Negative orientation would be the other way around, okay? So establishing that, then we can go to the theorem. So here's the theorem. Let C be a positively oriented, piecewise smooth, simple closed curve in the plane, two-dimensional space, and let D be the region bounded by that curve. So we have the picture that we just had. We have a closed curve, simple closed curve, C, with positive orientation that goes counterclockwise, right? And then let D be the region enclosed by that curve. Then this is true. Now, if you don't recognize this, this is basically kind of like your work integral. This is the same thing that we had before written in that second version where it takes everything to scalar form. But since we're in two-dimensional space, we're going to leave it as non-vector form. So somehow the line integral around over C of p dx plus q dy is equal to the double integral over d of partial q with respect to x minus partial p with respect to y dA. I'm just thinking about if I want to say this or not right now. No, I won't. Okay. So notice our integral symbol has changed a little bit. Notice the little circle around it, right? All that means is that you have a closed curve, that your C is closed. And if you don't put anything on the little circle, it's assumed that you mean counterclockwise, positive orientation. If you want to somehow change it to go the other direction, you can put a little arrow on that circle that puts it into the clockwise orientation. That would be negative orientation. Now, you can't truly appreciate this theorem until you see it in action, all right? So I'm about to do a problem with this theorem, and let me write it down over here. P dx plus q dy is equal to double integral over d partial q with respect to x minus partial p with respect to y. Does that look familiar to anyone? Mm-hmm. That part right there, dA. Does that kind of look something like this?
Yes.
Like if it's conservative vector field, like if we ever had a conservative vector field, then what would this be? That would be 0, wouldn't it? Okay, I'm just pointing that out, might come up later. All right, let's do this problem. Evaluate this line integral where our C is closed. We know it's closed because of that circle. Of y dx plus x dy, where C is the unit circle centered at the origin. I'm going to do this two ways. First without Green's theorem and then with Green's theorem. All right? So without Green's theorem, what we need to do is think about what these are. All right? So we learned last class, yes, that if we're going to do these line integrals, we first need to come up with some sort of parametric equations for C. So what are the parametric equations for C here? So if you go back and look at your notes, we were trying to find, this was before we got the vectors involved, because we were in two-dimensional space. We said C is some function, x is some function of t, y is some function of t. And in this case, if we want the unit circle centered at the origin, we can just do cosine t, sine t, right? And we'll let t go from 0 to 2 pi. That should draw us our unit circle. It'll draw it like this, won't it? Yeah. So that curve C is being drawn in positive orientation. And so visually, there's C, right? Okay. So this line integral becomes two line integrals. It's y dx minus line integral over C closed of x dy. So on this one right here, how would this integral be rewritten? Like, what does this mean? From 0 to 2 pi. So now we're going to actually put our limits of integration. What's y? Y is sine of t. Pardon? You see no vectors yet, right? No vectors yet. And then what's dx? Dx is the derivative of the x. So that's what? Negative? Negative sine of t dt. So there's our first integral, right? Everyone understand where that comes from? Okay, and then we have minus another integral from 0 to 2 pi. This time it's x, which is cosine t, times dy, which is a derivative of that, which is cosine t dt. And both of these are with respect to t, right? So I'm going to put them together into one integral. This is negative sine squared. This can be minus cosine squared. So I'm pulling the negative out completely. Negative integral 0 to 2 pi. And it would be sine squared t plus cosine squared t, which we know is 1, right? So negative integral from 0 to 2 pi of 1 dt. And when you do that, you should get negative 2 pi. So that's not terrible, is it? That's not terrible? Everyone understand the mechanics behind that? All right. But look at this. This is Green's theorem. It says if you're doing a line integral over a closed curve C of p dx plus q dy, that turns into this, right? Right? This double integral. So I'm going to go back to the original right here and write it down. Minus x dy. So we look at this and we say, all right, does our curve enclose a region D? It does, right? It encloses that. That is D, right? The region inside. So we're going to convert this line integral into a double integral using this formula, but we have a problem right now because this is a minus. And in the formula it's a plus, right? So I'm just going to rewrite this as y dx plus negative x dy, all right? So what is p? What is p for us in this formula? What is the p and what is the q? P is y, and q is negative x. Everyone good? So according to Green's theorem, this line integral should convert into the double integral over d of the partial of q with respect to x. What's the partial of q with respect to x? Partial of that with respect to x is negative 1. Minus, right, the partial of p with respect to y. And the partial of p with respect to y would be 1 again. D what? dA, right? Okay with that? Now that's just negative 2 double integral over d. So this is negative 2, right? I'm going to pull it out of the integral completely. And what would be left if I pulled that negative 2 out? Just dA, right? But I'm going to write it a different way. 1 dA. Yeah? And what is this? By definition, that is the area of D, which you can tell me without doing any more work, because this is the unit circle, right? This is the unit circle. This is 1. What's the area of D? Pi r squared, but r is 1, right? So this is just pi. The area of that's pi. So this is just negative 2 pi, and you're done. See, this work, you don't do this work. This work is just by looking. You look at it and you say, hey, look, the only other way to do this, to get to pi, is to set this up as a double integral, go to polar coordinates. But you don't want to do that. That's the whole reason this is great, because this is a nice region. We know the area of it. Okay, so let's just kind of take one step back. We had a line integral over a closed curve. We can use Green's theorem as long as we enclose a region. We have to rewrite it to look like line integral of p dx plus q dy. We do our partials. We got something really nice, pulled it out. This was the area of D, and we knew that visually, boom, like that. If we had to run through that problem again, it should take us like less than 2 minutes, right? But you may be like, I don't know, man. I'm okay with that other way. Maybe you're just not sold. I'm here to sell you. Okay?
I don't look sold for that.
Okay, so let's try and get this one set up. We'll do it the first way without greens, and then we'll do it with greens. And I think we're going to submit pretty quick, pretty early here. All right? All right, so if we do it the old way, we look at our curve, right, C. Our curve C here is x squared plus y squared equals 9, which is circle of radius 3. Okay, so I know that my C here that we're looking at is this thing. If I orient that this way, then I could go through and set up my parametric equations. X is some function of t. In this case, it would be 3 cosine t, and y here would be 3 sine t. The 3 is coming from the radius of it, right? I should put that, that's 3. And I know my t goes from 0 to pi. So that part's not too bad. It's the next part, right? Because now what I'm going to have to do is rewrite these, right? Oh my goodness gracious. So this is going to become 3 times what? 3 sine t minus e to the sine of 3 cosine t. And then dx, which is the derivative of x, which is negative 3 sine t dt. That'll be my first integral. My other one will be 7 times 3 cosine t, square root of 3 sine to the 4th. Ooh. Right? Does that just look terrible? That looks terrible, right? But because we have a region in here that's enclosed, D, we can go to Green's. We just need to identify the P and the Q. Here's our P. Here's our Q. Do we have a plus between them? We do have a plus, so we can go right to it. So this will be equal to the double integral over D. What is the partial? We start with the partial of Q with respect to X. It's just 7, right? Partial of Q with respect to X is just 7. 7 minus partial of P with respect to Y. 3. dA. That's just a constant, 4. Wait. Yeah, sorry.
I'm just confused how you got 7 3 real quick.
Okay, I'm using this formula, right?
Okay.
So partial of Q with respect to X, this is all Y's, it's gone, 7.
Got it.
And then this one with respect to Y, 3.
Got it.
So this is just 4, I'm going to pull it out of the double integral over D of 1 dA. And again, that's just the area, that's the area of D, which we should know by just looking at that. The area of that circle is pi r squared, right? So this is 4 times pi times, what's the radius this time? 3, so 3 squared, which is 36 pi. I mean, I don't even know how bad that integral would be. I mean, I'm not sure we could do that integral by hand. I mean, I'm pretty sure we couldn't. I'd be tempted to put it into Wolfram Alpha to see what it did. Isn't that clean? Isn't that nice?
I submit.
Yeah. So, you know, there will be a problem on a take-home test or something, or on one of your mini exams, or on the final where I'm like, you know, hey, do this line integral, and someone's going to go do the line integral, and they're going to spend 35 to 40 minutes doing the line integral when they could have used Green's theorem and just did it in a few minutes. I'm not going to prompt you for it. I'm not going to be like, use Green's theorem to do this. You've got to recognize it. You've got to say, okay, wait a minute, you know. I could do this one way, but because it looks like this, I can use Green's. The thing that should tip you off is you've got a closed curve, okay? I mean, if your curve is not closed, green is off the table, all right? Now, hopefully I've convinced you that sometimes computing the line integral over a closed curve is easier when we use Green's theorem, right? But there are cases where we can actually go the other way, where we can have a double integral that we're trying to find, and we can use the line integral to compute it. Now this is tricky. Maybe we should take a break right now, because I need you to kind of clear your minds a little bit before we do this. You think it's a good time for a break?
Yes.
3:30? We'll go, what, 3:40? 3:45? You want 15 or 10? What do you want?
I'll take 15. I'll take 30.
30? 15? We'll go 15. 3:45.